Hello, and thank you for joining us today. This is, of course, one of the user presentations within the frame of the IPERION Heritage Science Project in collaboration with the European Research Infrastructure for Heritage Science. And we have the pleasure of introducing a very exciting project to be presented by our Spanish colleagues. My name is Matthias Sterlich, and at this point, I would like to hand over to our colleague, Antonina Chaban, to manage and host this particular presentation. Over to you, Antonina.
And we thank you so much for joining us today. As you probably know, we are hosting the last IPERION HS Transnational Access User Meeting event. This time, it will be dedicated to a very successful Molab project, one of those that we had recently, and we will invite our speakers to present their project. It's over to you, Raquel, Marta, Cristina. Please, if you can present yourself and if you can introduce us to your Molab project.
Hello, thank you very much for the presentation. Thank you for joining us. I'm Raquel Freixas-Jambert. I'm a PhD student from the University of Barcelona, and my research field is about the identification of photographic materials. So this talk is a little part of my thesis, my doctoral thesis.
Hi, my name is Marta Oriola-Folch. I'm a professor in conservation, paintings conservation at the Faculty of Fine Arts at the University of Barcelona. And I'm one of the three PhD directors Raquel has. So that's why we are here. And Cristina, this is to you.
Hi, everyone. Thank you very much for the invitation. I'm a paper conservator. I'm a professor, and together with Marta at University of Barcelona, teaching paper and parchment conservation, and I had the great pleasure of being one of the directors of the PhD Raquel was developing.
So we can start the presentation talk. Okay, I'm going to share the screen. Just wait a moment, please. Okay. So, sorry. Okay, I think now you can see it clearly.
Yes, perfect. We can see it.
Okay, thank you very much. So, first of all, as I said, so it is necessary to explain that this project stems from a PhD research that aims to establish the key identification features for photographic oil positives, bromoil, oil, and bromoil transfer using non-invasive methods. So therefore, the Molab data could be interpreted thanks to all the knowledge generated in the doctoral thesis. Therefore, all the slides containing results derived from the thesis will be indicated. So, but in our institution, we only had access to benchtop Raman and FTIR equipment that were suitable for our proposals. So this type of equipment caused problems in measuring a significant part of the samples due to their large format, up to 50 per 70 centimeters, since the benchtop equipment is designed to analyze small laboratory samples, not artistic objects. So on the other hand, we could not regulate the environmental control of the analysis room, and most importantly, we did not have access to X-ray fluorescence equipment suitable for our project. In short, it's for this that the Molab infrastructures facilitate a study that would have not been possible, or at least not with expected results. For these reasons, the main purposes of this project was to apply FTIR, Raman, XRF, and UV visible infrared spectroscopies with mobile equipment, to expand the knowledge about the constituent materials of the objects, to ensure optimal analysis conditions, and to compare and supply the limitations of the benchtop equipment we had available. On the other hand, it is very important to mention that there is no reference in the literature of these analytical techniques having been specifically applied to oil processes, although they have been proven to be useful for other types of photography. mainly supervised photographs. Therefore, this project fills an existing gap, enabling a more precise identification of oil positives, as well as providing detailed information on their composition and its possible degradation mechanisms. Now, we will develop the details of the project, but first of all, let me briefly introduce you what oil photographics are. So, these types of photographs are created by what are known as oil pigment processes, which, as the name itself suggests, contain greasy inks to create the image. This family of oil processes is comprised for the oil and bromoil process and their respective transfer, so oil transfer or bromoil transfer. At this point, it is necessary to explain that when I say oil processes or oil positives in plural, I am referring to the family of bromoil, oil and transfer prints, so that photographs with an image made of greasy inks. But when I said oil process or oil prints, I am referring specifically to the Rawlings oil process. So in the following slides, I will explain in more detail each of these photographic processes and their differences. Before going into more detail, it is important to explain that the oil processes are also included within other larger categories. Firstly, they are part of what are known as pigment processes. These are photographic techniques that use pigments instead of silver salts to create the image. These processes offer a wide range of artistic expression and are especially valued for the durability and aesthetic quality of the resulting prints. Some of the most well-known include carbon print and its variants like Fresson, or also gum bichromate prints or platinum prints. Within the family of pigment-based prints, moreover, the oil pigment processes are included in the category of dichromated processes. These techniques introduce a dichromate, that is, a chromium salt, as a light sensitizing agent, mixed with a colloid as gelatin, gum, or a starch. However, the most important difference is that the oil pigment processes are the only ones that have a greasy medium, mainly linseed oil, to bind the pigment particles to form the image. These photographic processes were developed in the early 20th century as a result of decades of research and experimentation in search of the definitive novel process. It could be said that oil is the first successfully applied oil pigment process, but bromoil method represents an evolution and improvement of Rawlings oil process. The oil-positive processes were very relevant for pictorialist photographers in the early 20th century, enabling them to merge art and photography through manual manipulation to create images that transcended mere visual representation. Key figures of the time, such as Dr. Plagianini, played a crucial role in the dissemination of these photographic methods. Considered one of the most representative figures of Spanish artistic photography, Joaquim Plagianini was a master of bromoil and bromoil transfer processes, techniques that allowed for unique blend of textures, depth, and artistic expression. Today, prints produced through these processes are part of large collections at museums and institutions around the world, attesting to their high artistic and cultural value. So, let's talk about what is the bromoil process. So as the name suggests, the word bromoil, okay, it's composed of brom from silver bromide and oil from the oil of the greasy ink. The process begins with a photographic copy on silver gelatin, usually a silver bromide print exposed with a photographic enlarger or by contact, developed, fixed, and washed as usual. It should be noted, however, that it requires papers with very specific characteristics and the use of products without hardeners. During development, the silver halides in the emulsion are converted into metallic silver to create the image. The second and most important step is the bleaching bath, where the bromide print is immersed in a chemical solution containing 4 basic components. Potassium dichromate, which hardens the gelatin in proportion to the amount of silver eliminated, potassium bromide, which reduces metallic silver back to silver salts, copper sulfate, which reduces dichromate and acts as an energetic insolubilizer, and hydrochloric acid, which accelerates the bleaching process. This solution has 2 simultaneous effects. It converts the metallic silver in the gelatin emulsion into silver salts, so the image disappears, and it hardens the gelatin layer in proportion to the amount of silver. So the black areas of the original image will be hardened gelatin, while the white areas will be unhardened gelatin. After bleaching, the paper has lost the silver image, is washed in water and fixed with a solution of sodium isosulfite to remove or dissolve the residual silver salts. The well-bleached and washed paper is placed in a hot water hydration bath to convert the gelatin paper into a matrix. The hot water hydrates and swells the unhardened gelatin, so the whites, and proportionally the middle tones. On the other hand, the areas of gelatin that are hardened during the bleach bath, blacks and middle tones proportionally, do not absorb water. So the result is a gelatin matrix, which is inked with engraving or lithographic inks in order to reproduce the image that was originally on the silver bromide copy, but this time with greasy ink. This process is based on the lithographic principle that oil and water repel each other. So when the oil ink is applied with a special brush, the hydrated gelatin repels the oily ink, while the hardened and non-hydrated gelatin accepts the ink, forming the blacks and middle tones of the image. The matrix can be hydrated and inked several times until the desired final image is achieved. The great advantage of this process is that it allows enormous manipulation of the image from the beginning of the process, as well as the application of a large number of subsequent retouching techniques at the end of the process. So, the knowledge and understanding of the production process is essential in order to understand the physical and chemical transformation that the copy undergoes during the process, as well as the substance involved. In order to define how is the stratigraphic structure of a bromoil or bromoil transfer print, it is necessary to know which is the purpose of each step in the production process. Thanks to this prior knowledge, it is possible to make a first hypothesis about the final material structure of the object and to predict which compounds and elements might be present. Recognizing this stratigraphic structure at the basic material is the key to considering the most appropriate analytical techniques to study the object, establishing an effective analysis methodology, and selecting the most appropriate measurement points, as well as anticipating the type of information that can be obtained depending on the location of the analysis point. So then in this slide, I will show you some diagrams, okay, that illustrate the physical and chemical transformation that the silver gelatin copy undergoes throughout the process until the final bromoil is obtained. It is presented from 2 points of view. Tangential, okay, to see what the stratigraphic structure of the copy looks like, and genital, to observe how these changes are reflected in the photographic image. This first diagram shows the basic structure of a silver gelatin print consisting of a paper support, a layer of baryta, okay, which may or may not be present, and a gelatin emulsion that contains the silver particles that make up the image. If we look to the right, the black areas of the image are where there is more metallic silver, and we call them the max areas. The middle tones or grays, called the mid areas, have less silver particles, and the white areas or the mean areas have almost none. When the copy is bleached, the main thing is that the metallic silver is removed, that is, the image disappears. And at the same time, the gelatin hardens proportionally to the amount of silver present. It means that the black areas are hardened and the white areas are not. When are hydrated in a hot water bath, the white areas or unhardened gelatin swell with water to form a gelatinous relief or matrix, while the D-mean areas swell in proportion to their degree of hardening, and the D-max areas do not swell. So then, when we have the matrix of hydrated gelatin, we apply the greasy ink that will inform the final image. As we have said, the ink will adhere to the hardened, non-hydrated parts of the matrix, forming the whites in the, forming the blacks in the image, while it will be repelled by the hydrated areas, forming the whites in the image. We notice that when we have the image in the final bromoil, The pigment particles that form the image are not inside the gelatin, but they form a new superficial layer of ink that wasn't there originally. Oh, well, not to get too carried away, the process of bromoil transfer is basically one step further than the bromoil process. A bromoil copy can be conceived as the final result, or if it's desired, the ink image can be transferred to another support, as usually high-quality paper, using an engraving press to produce what is known as bromoil transfer print. The advantage of bromoil transfer process is that it allows to print different matrix on the same paper support to create new image, as well as combining matrix inked with different colors to create polychrome image. At the bottom right of the slide, I leave a link to a video we made for the Museu Marítimo of Barcelona, which shows the whole process of making bromoil and bromoil transfer print. Okay, then this change of support due to the transfer of the greasy ink onto a new paper completely changed the structure of the work. The only thing that remains more or less the same is the material forming the image, which in this case rests directly on the fibers of the paper. During the transfer, the image also is inverted, okay, as you can see here. In other words, we go from a support containing of at least 2 layers plus the layer of ink to support consisting of a single layer, mainly cellulose, plus the ink layer. It is obvious that the structure, material composition, and visual characteristics of bromoil prints and bromoil transfer prints will be very different, even though they come from the same manufacturing process. So, the oil process was the predecessor of the bromoil process. I will explain it very quickly because it's not very common and it's easier to understand. It consists basically of a gelatin-coated paper that is treated with a dichromate sauce solution and then is contact printed under a negative of the same format. Unlike bromoil, the oil print was limited to the same format as the negative, as it could only be exposed by contact, so under UV light. The dichromate salt generates a differential hardening of the gelatin, which, when it's hydrated in a hot water bath, as well as in the unhardened areas, creating a gelatinous matrix. This matrix, after, is inked with the greasy inks and the oil copy is obtained. So an oil transfer is exactly the same as a bromoil transfer print, but using an oil print as matrix, okay? So papers for the oil process could be made by hand, but were also commercially available. But distinguish between oil and bromoil prints can be very difficult. So generally, oil prints tend to be smaller than bromoil prints, and the paper fibers are more pronounced due to the lack of vertical layer. But there may be exceptions that it would be possible to make an oil print by reusing or recycling a bromoil paper. In these cases, it is extremely complicated to differentiate between both processes, even analytically speaking. To illustrate this, I have included this diagram showing the different types of support we can find for oil and bromoil print. Well, the usual support of the oil process, okay, in the middle, is a common paper with a gelatin layer. This cannot be used for the bromoil process, but we can see that it is possible to make an oil print by reusing silver bromide or silver chlorobromide paper, even if it's not the most common support. Okay, if we talk about the state of the problem and the general proposals of the project, firstly, we have to say that there is a big lack of scientific studies of oil processes, both technical and morphological. There are cases where instrumental analytical techniques such as FTIR and X-ray fluorescence and Raman spectroscopy have been successfully applied to different types of photographic materials. But on the other hand, there are no precedents for the analytical study of bromoil transfer, and oil prints. So the most common system for the identification of photographic processes is to study the morphological characteristics of the print. But this system does not allow for in-depth knowledge about the physicochemical nature of the object or the mechanism of degradation. In addition, there is often a confusion between bromoil and other photographic processes that produce prints with similar characteristics, such as carbon prints, oil prints, gum dichromate prints, gelatin silver prints, and others. On the other hand, we have to refer to primary source of information like manuals, receipts, and specialized magazines of the early 20th century in order to better understand the technical and compositional aspects of these prints. However, is it not clear what compounds actually make up these photographs? That is an aspect of great importance for their conservation. So finally, it shows how all this lack of knowledge ultimately leads to serious problems of identification and conservation of these photographs, even though they are often part of collections of important museums and institutions. So for all these reasons, the general aims of this project are to know the compositional structure of oily prints, to use advanced not invasive identification techniques, obtain detailed and specific compositional data, identify the limitations and potential of the different techniques and equipment used, and compare results from mobile equipment with previous data obtained from benchtop equipment. We believe that these projects will make it possible to complete the results and data obtained during the research of the doctoral thesis and to generate a detailed compositional and morphological profile for bromoil, oil, and transfer prints. So during the project, we studied 23 original bromoil transfer and other positives as silver gelatin and Fresson prints from 1920 to 1970 by Dr. Plagianini, the main exponent of Spanish pictorialism. The works were from the Museu Marítim de Barcelona and from the artist family collection. So we also have access to a contemporary oil positive by another artist, as well as laboratory samples as bromoil, oil prints, and matrix that we made from the original receipts, and we used them for comparison. Okay, so in this slide, there is specific information about every equipment we used during the analysis. I go a little more. Okay, so if we talk about the analysis method, we studied at least 9 spots per work per technique, 3 points in areas of minimum image density, 3 points in maximum density areas, and 3 points on the verso. The IMAX measurements will give us mostly information on the image forming materials as pigments, linseed oil, or image processing elements. The main measurements will provide us with information from underlying materials like varietal layer, photographic binder, or the support. Comparison with the verso measurements will indicate if the materials are part of the photographic process, so if are image processing materials or are part of the support, including the binder, the varietal layer, or other intermediate layers. If it was possible, we also made measurements in the medium image density areas. So it was also necessary to set up a support system for the works according to its equipment. For the X-ray fluorescence, the works were placed on a transparent methacrylate plate with the help of corners and holding strips made of conservation polyester known as Malinex, which was also mounted on an earball. The system of corners made it possible to change the methacrylate plate quickly and to adapt the fixing system to the size of each work. The same system was used for FTIR spectroscopy, while for Raman and UV visible infrared spectroscopies, it was sufficient or enough to place the work on a conservation cardboard and hold it with glass weights. So, while the X-ray fluorescence analysis had to be carried out in a separate, I get lost, sorry. So, well, to streamline the work and complete the major part of the work during the 4 days we had the Molab, we devised a rotating work system so that X-ray fluorescence, FTIR, and Raman spectroscopies analysis could be carried out simultaneously. Separately, in the last session, UV visible infrared tests were carried out. The working method consists of assigning one technician to each analytical technique and a team of 2 people dedicated exclusively to preparing and assembling the samples and recording which analysis each sample had undergone. The cycle begins with assigning a sample to each of the 3 techniques. As the analyses were complete, the sample were rotated to the next technique until the entire cycle was completed. When a sample completed the analysis cycle, it was stored and another was prepared. The sample preparation team was always active, so the analysis cycle never had to be stopped. Then there was one person, in this case me, who was responsible for monitoring the analysis points and the analysis process for each technique. Each measurement point carried out by each equipment was recorded in the MOVIDA software on an individual map for each work. Here you can see an example. MOVIDA software allows to store and correlate all the data obtained during the analysis, visualize the maps with the measurement points, compare spectra, enter the instrumental characteristics, and other functions. So, if we start to talk about the results, below are some of the most significant results achieved with the Molab equipment, but we cannot go into all the results because this will be a very long talk, but we will present some of the most relevant. One of the most significant results was the detection of the varietal layer by reflection FTIR spectroscopy, as this was not possible with the benchtop instrument because the barium sulfate bands were outside of the spectral range. So, on the other hand, with the mobile instrument, barium sulfate could be identified thanks to combined bands appearing at 2,200 to 2,000 centimeters and the bending modes appearing in total reflection mode, okay, as inverted bands close to wave numbers 615 and 640. Furthermore, the detection of the barium sulfate signals is inversely proportional to the density of the image. That is, it is well detected at the mean areas, okay, as we can see in the spectrum, partly at the mid areas and very little or not at all at the max areas. This is due to the presence of the ink layer in the image, which limits the access to the lower layers as the image density increases. With Raman spectroscopy, we were also able to confirm the presence of barium sulfate in many of the bromoil prints. Barium sulfate is quite intensely detected by Raman, and as with FTIR spectroscopy, its intensity is inversely proportional to the image, as we can see in the spectrum. Okay? So, X-ray fluorescence is a technique that was also very effective in the detection of barium and sulfur from the varietal layer. It was often the element detected with the highest intensity. It should be noted that X-ray fluorescence has a greater ability to penetrate than FTIR or Raman spectroscopies, which are surface techniques. This means that barium from varietal layer, being a homogeneous layer, will be detected more or less uniformly in all the points of the sample, as the layer of greasy ink in the image does not affect the ability of the XRF instrument to detect the underlying layers. In this case, what allows us to confirm that the bariums come from an intermediate layer was the minimal presence of this element on the back of the primary support, as seen in the spectrum. So you can see the spectrum of the support is the yellow spectral line, okay? One of the greatest discoveries during the project, also thanks to elemental analysis with the X-ray fluorescence, was the detection of specific elements from the chemical baths. In the case of bromoil prints, it has been confirmed the presence of chromium, okay, and copper is closely linked to the chemical bleaching baths. These elements have been detected to a degree proportional to the image density. So Raman and FTIR spectroscopy were also useful for the detection of pigments in bromoil oil and bromoil transfer prints, mainly carbon black, iron oxide pigments, and Prussian blue. If we see the FTIR spectra, we detect Prussian blue in the Dmax areas of the image of this bromoil sample, thanks to the strong absorption band at approximately 2090 due to the triple bond between carbon and nitrogen. If we see the Raman spectra, we detect the carbon black and Prussian blue in the Dmax areas of the image of the sample. Carbon black is identified by its characteristic Raman band, palette D band, and G band, and we can also identify a small bands of Prussian blue near 2150 and 2100, but the low resolution of the spectrum makes its localization very difficult. The same happens with the Prussian blue bands that appear in the lowest spectral range. They are not well seen due to the spectral noise, so I could spectral in this link. With the FTIR spectroscopy in reflector mode, we could also identify the iron oxide based pigments from some of the bromoil image, thanks the two inverted bands in the range of 670 and 400 corresponding to the iron oxide extraction mode. Its X-ray fluorescence has been very effective for the detection of pigments thanks to elemental identification, especially for the iron oxide pigments, like to distinguish between sienna or amber. For example, if we see the two spectra of the left side of the slide, on the left, there is a XRF spectrum of the D-min, D-mid, and D-max point of a bromoil sample, where we can see an iron signal clearly proportional to the image density. On the right, there is a X-ray fluorescence spectrum of the D-min, D-mid, and D-max points of the same sample, showing a small amounts of silicon proportional also to the image density. So the high intensity of the iron and the low intensity of silicon, both proportional to the density of the image, plus the absence of manganese, indicates that this pigment is burnt sienna and discard burnt amber. On the other hand, the spectrum shows localized iron signals in another sample proportional to the image density. In this case, the iron is originating from Prussian blue pigment, and we know this because we can corroborate this result also with FTIR and Raman spectroscopy. So another aspect of the analytical study was to confirm the fatty nature of the ink that formed the image. Until now, FTIR spectroscopy has been the only non-invasive way of detecting fatty oils in inks. We were able to identify the fatty oils in the Dmax range thanks to the appearance of the carbonyl band and the carbonyl band that's characteristic of fatty oils and the formation of carboxylic acid products related to the polymerized state of the oil in the older samples. So, spectrum below, shows the result of the FTIR's analysis of an ancient bromoil print. If we see the blue spectral line, a contemporary oil print, the yellow spectral line, and an ancient bromoil transfer print, the red spectral line. Note that in the oil print, the yellow one, has a band at 1745 is clearly distinguishable. It corresponds to the carbonyl group of the drying oil. In the spectrum of the bromoil print, this band is merged with a new band appearing at 1715, which is the result of the formation of the carboxylic acid products due to the aging and polymerization process of the oils themselves. Finally, the imprints in the bromoil transfer prints are the ones that have given a milder signal. The characteristic sinks of the oils no longer appear as defined bands, but rather as rings or small bands. This is due to the absence of a binder to separate the ink from the cellulose support, which absorbs oil much more due to its high porosity, thus producing a less intense signal from the linseed oil. So in the course of our research, we have used advanced technology, including portable FTIR spectroscopy, Raman spectroscopy, and X-ray fluorescence to carry out detailed analysis of various samples. Using these methods, we have obtained significant results that allow us to improve our understanding of the materials studied. One of the key results of our study was the detection of the baryta in the bromoil samples. This was achieved through the use of a portable FTIR spectrometer, which give us a wider spectral range than the conventional laboratory instruments. We also complemented our analysis with Raman spectroscopy and X-ray fluorescence, essential tools for the precise identification of varietal layer components. Another finding was the identification of the protein binder in the bromoil and oil prints using FTIR spectroscopy. In addition, we were able to identify key elements from the image processing using the X-ray fluorescence. This finding provides valuable information about the methods used to produce these photographs. And throughout this study, we faced the challenge of using mobile equipment for the first time in this type of works. So among the advantages we found, we highlight the portability and flexibility of these instruments, which allow us to perform in situ analysis in controlled environment and study different collections at the same time. This kind of techniques also guaranteed a safe measurement process for the works, so that a not invasive method, and allowed to carry out multiple analyses at the same time in the same workspace. Sorry. However, we also encountered certain limitations, including the precision and sensitivity compared to the conventional laboratory equipment, especially for the Raman spectroscopy. It is also important to mention that UV visible infrared showed no significant results. Despite this challenge, we believe that the use of mobile technology has considerable potential for future research, as long as its capabilities and limitations are taken into account. So in conclusion, general results were very satisfactory and allowed to meet all the expectations set by the project. These data were later extremely useful to compare with results of the analysis from the benchtop equipment, as well as the morphological study. And more important, the results were consistent in all areas, which is considered a success. Nivotrap results have been compared, crossed, and combined with all other data resulting from the PhD research, what has allowed the development of a super complete and a specific identification profile of the bromoil transfer and oil positives. These results will be communicated in a couple of months in the PhD defense and submitted to publication afterwards in scientific journals. Finally, our study demonstrates the effectiveness and value of using advanced analytical techniques, including mobile equipment, for the identification of photographic materials. The results not only contribute to our current knowledge, but also pave the way for future investigation in this field. Here, there's a link of a video that made our colleague Claudio from the Molab team, which gives an overview of all the work carried out during the Molab week, and it's available in YouTube, okay, on YouTube. And to close the talk, thank you very much for your attention, and to all those who have made this project possible. So thank you very much.
Thank you very much, Raquel. It's really very impressive. Thank you. Thank also Marta and Cristina, who are supervising this amazing and very complex work. If I may ask you, Raquel, if you can kindly stop sharing the screen.
Sorry, I stopped saying.
Excellent. Excellent. So thank you very much. Let's give maybe a few minutes to our audience to write down their questions. And for sure, Raquel, Marta, and Cristina will be here to answer, to give the answers to all the questions that will arrive now. I just have a very short communication at the end of this meeting. So first of all, as you probably know, this is the last IPERION HS User meeting event, and we would like to thank you all, to thank our audience for following all the 5 IPERION HS User meeting events of the season 2023-24. Of course, the HS Academy events do not stop here, and very soon, just in 2 weeks, on the 28th of March, we invite you all to follow the next HS Academy lecture. The next lecture will be given on the topic dendrochronology, tree rings, Art and Archaeology, and this will be delivered by two speakers, Pascal Freiture and Vincent Labat. So we will be glad to welcome you at this event and to all the other events that are still coming. Stay tuned.